So what we're now going to move on to is another aspect of experimental analysis. This isn't concerned with statistical properties that we've been looking at in the last two lectures. It's concerned with presentation of experimental results. So in particular, with a certain aspect of a subject called data analysis, and in particular, how we can display, how we can show results in a clear form using a method called regression. So here's some background to that problem. We have carried out an experimental study, and as a result of that we have a set of observations we've gathered from a set of data. So for example, this could be something such as the average time we've observed that a program takes on a particular range of input data. And the question we're interested in is, how do we present our results in a manner that is effective and clear? Well, we could use a table to do that. We might have a table with a number of columns, one of which presents our data values and the other of which presents the observations that we've seen for those data. The problem with using tables is if we have a lot of material in our experimental outcomes, the table might be extremely lengthy. Furthermore, sometimes we are using tables for which two columns aren't sufficient to present our data, and therefore the more columns we have, the actual nature of the table and what it's claiming to demonstrate may be very unclear. So tables, they're reasonable for small amounts of data, but once we start getting much larger quantities, they're not really suitable. So what's the alternative? Well, we could try and draw our results on a diagram. So one way of doing that is to present a plot or a curve on a standard coordinate axis. And now we have the problem, which is the one that we're going to be looking at in this lecture, of how do we find the best fitting curve, the best fitting line. So as I said, that's the topic I'm now going to look at in this lecture. So here's an example. We have a table of observations which we've seen when we used a particular set of values. The table might be something like this. Here are our data values, and here are the observations that we've seen from those data values. Now, how do we best describe this data set as a plot on a two-dimensional axis? We could choose this solution. So here we have a line, the points of the data that we have in this selection here, and this is our line which we claim fits that data. It appears, maybe to underestimate what's going on. Here's another way we could fit a function to that data, and this seems to be a lot more accurate. The points we have are actually lying on the line that we've chosen, on the function that we've chosen, unlike this case where most of these are lying away from the line that's being used. So before we can continue to look at this, the first thing we have to do is to establish what do we mean by the best fit. Now, the standard interpretation that's used in this area is an idea called least squares approximation. So the interpretation is that the best fit line, the best fit function, is the one that satisfies this minimizing least squares criterion. So what do I mean by that? Well, go back. We have our set of data and observation pairs here. And what we're looking for is the function over the real numbers that best describes these data observation pairs. And what we mean by best function is the one that minimizes this expression. We add up over all of our data the observation that we've seen, but we subtract from that the function that we are using to try and approximate our data when we plot it. And in order to ensure that we have a non-negative outcome, we square all of these terms. So we have the observation, the amount that observation differs from the approximation we're trying to find, all of that term squared, and we add up all of the results. So what we're trying to do is to find a choice of function that minimizes this expression. Well, we met line functions on a number of occasions in the past. They are not ideal in terms of the outcomes that we will see as approximations, but they very often provide strong support for a particular claim. The other advantage that line functions have is we can find the best fit line function in the sense that I had on the previous slide. We can find that quite easily. Now, there are other classes of functions we may have arising. However, it very often happens that we can make some simple manipulations with our data set, and these allow us to capture the function that we're looking for in terms of finding a best fit line function. So let's go back to an issue we looked at earlier in the course. What exactly do we mean by a line? Well, as we saw when we introduced our study of differential calculus, a line is just a function of its input values which is described by two parameters. So something of this form. We have this parameter which we refer to as the gradient of the line, and this parameter which we refer to as the offset of the line. So when we talk about finding the best fitting line for a set of data, all we mean is we are looking for the best pair, the pair that we can select as the gradient and the offset, which will result in our least squares approximation being minimized. So how do we combine these? Let's look at what we had. We have our data and observation pairs, this collection here. What are we looking for? We are looking for two constant values, a gradient and an offset. And when we use these two constant values in our line function, the outcome will be to minimize this expression here. So we have this function of our two variables, and that value of that function is given by summing over our observations the result of applying our line function to the data value that we started with. And we're going to square all of that term. So we're looking for a choice of these values which will minimize this expression. I should point out that the data and the observation values are constants. So this function is not a function of the data that we've been using. It is solely a function of these two parameters here. Now, we know how to solve that problem. We know how to find the choices of gradient and the choice of offset that will minimize this expression, because that's something we saw earlier in the module. This is in effect a partial differentiation problem. So it's going to involve taking the partial derivative of this function with respect to one of the variables, taking the partial derivative of that function with respect to the other variable, and finding the critical points that result. So let's look at what happens when we do that. We find that the best fit line function is this expression here. I'm not going to work through how exactly we get that. I'm just going to quickly run through the notation that's being used here. So what do we have? This notation indicates the sum of our data values. This notation is the sum of our observation values. We also have the sum of the squares of our data values and the sum of the component-wise multiplication of each data value with its corresponding observation value. So we have that shorthand. We plug those terms into this expression. N here is the total number of data observation pairs, and this function turns out to be the best fit line function for our data. So this term gives the gradient of the line, this term gives the offset of the line. As I said, I'm not going to work through the exact derivation of that. If you don't feel quite happy with your understanding of partial differentiation, then I suggest you work through that exercise for yourself. What about other functions? Not everything is best described by a line. Well, we might need to look at functions such as power functions, where we have some constant value multiplied by our input raised to a power. We might have to look at exponential functions, where we have a constant value multiplied by another constant multiplied by our input value, and that whole outcome exponentiated. We might have logarithmic functions, or what are called linear rational functions. We may, in fact, have more than one parameter we need to optimize. So, for example, if we're dealing with trying to find the best fit quadratic function, here we have three parameters. We had the gradient parameter that we had before, the offset parameter that we had, and their final coefficient parameter. So if we're looking for the best quadratic function, then we're looking at finding the best choices of our three coefficients in the quadratic expression. Now it turns out those cases aren't too difficult to deal with. So although in principle we could just use exactly the same approach of forming partial derivatives and looking for critical points, they are easily dealt with by doing some rewriting. That manipulation is described in the textbook, so I'm not going to go through it here. The cases where we have three or more variables, these become quite onerous to work with. So the quadratic case, what is called quadratic regression, that is just about feasible. Again, that's something that's described in the textbook. as we move to larger numbers of parameters, we end up with quite involved problems involving partial derivatives with many variables. What about other data analysis matters? Well, one of the common objections to the sorts of techniques I've just been describing is they don't impose a requirement that the approximating function exactly matches the data and observation pairs. So where we do want to have such a fit, there are various methods which are around. One of them is called Lagrange interpolation, which finds the best fitting polynomial function for a set of data. There is another form of curve fitting. So I've been looking mainly at polynomial style expressions. There is a subject which is of significant importance in electronics and in signal processing, which involves interpolating trigonometric functions. So we're trying to find the best fitting curve as some sum of sine and cosine operations. A lot of the ideas that you'll see with those occur in later computer science modules that you'll see next year. So I won't give any further detail on those. And that sort of concludes the coverage that we have of experimental methods in computer science.